So right now, somewhere hundreds of miles away, there is this massive cylinder of solid steel, and it's spinning at like over 3,000 revolutions per minute.
Yeah, it's incredible.
And it's completely surrounded by highly flammable hydrogen gas.
Yeah.
And if it stops spinning for even just a few seconds, well, the screen you are looking at right now just goes totally dark.
It is, I mean, it's a really profound disconnect. We demand instant power at all times, right?
Hmm.
But we are completely blind to the violent, roaring, just deeply physical reality that is actually required to generate it.
Exactly. I mean, you walk into a room, you flip a plastic switch on the wall, the lights come on, and that is just the end of the transaction in your mind.
We treat it like magic.
We really do. We treat electricity like it's just pure magic. We never think about the fact that at that exact millisecond, a massive hunk of spinning metal had to physically shove that energy through a wire just for you. But today, we are making the invisible visible. Welcome to this deep dive into the hidden world of electric machines. Our mission today is to demystify the massive, complex equipment that silently powers your entire modern life.
And our guide for this journey is a phenomenal source. We're looking at Ashfaq Hussein's comprehensive engineering manual. It's called Electric Machines.
Right.
And it provides this brilliantly detailed look into the fundamental physics and, honestly, the sheer engineering audacity that keeps the global grid online.
Yeah, we're taking you on a full journey today. We're going to start at the power plant where electricity is been literally born, figure out how these massive spinning rotors don't just tear themselves apart, and then unpack the desperate engineering required to keep these machines from melting down.
Which is a huge part of the design, yeah.
Definitely. And finally, we'll explore how Transformers managed to safely deliver that raw, lethal power to your home and to, massive industrial manufacturing plants.
So let's start right at the absolute source of it all, which is the synchronous generator, or what engineers commonly call an alternator.
Okay.
At its core, the fundamental job of this machine is to convert mechanical energy, like a spinning water turbine or a high-pressure steam turbine, into alternating current, or AC electrical power.
Okay, let's unpack this for just a second, just to keep our bearings. An alternator is essentially doing the exact reverse of an electric motor, right?
Pretty much, yeah.
Because a motor takes electricity out of the wall and turns it into mechanical movement, like spinning a fan blade. But an alternator takes the spinning movement from nature and, forces it into electricity.
Precisely. They are two sides of the exact same electromagnetic coin. In fact, mechanically, a synchronous generator can often even be run backward as a synchronous motor.
Oh, really? That's cool.
Yeah. But what is truly fascinating here is a specific, just brilliant design choice made for modern, large-scale alternators.
What's that?
Well, in the early days, or even today in very small generators, you would generate power by taking a heavy coil of wire, which is the armature, and spinning it rapidly through a stationary magnetic field.
Right, that intuitively makes sense. You spin the wire through a magnet and you, extract the juice out of the wire. But wait, what exactly is an armature? That's a bit of heavy engineering jargon.
Ah, fair point. The armature is simply the part of the machine where the actual electrical power is generated.
Okay.
It's the main coil of wire that will eventually feed the power grid. Now, in massive utility-scale alternators, engineers realized pretty quickly that spinning this incredibly heavy, high-voltage coil was a terrible idea.
I can imagine.
So they flipped the script. They keep the massive armature completely stationary. They literally bolt it to the floor, and it becomes what's called the stator.
Stationary, got it.
Right. And instead, they take the magnetic field and rotate that inside the stationary coils. That rotating magnet is the rotor.
Okay, so that makes so much more sense. Imagine you're trying to generate energy, and your setup is an incredibly heavy, thick copper coil of wire and a separate magnet.
Yeah.
Instead of trying to violently spin this 1,000-pound high-voltage coil of wire around your head while awkwardly trying to tap electricity off of it, you just bolt the heavy coil perfectly still to the floor, and you spin a lightweight magnet really fast in the middle of it.
That is a perfect way to visualize it.
Yeah.
And the physics behind why this stationary armature design is so vital really just comes down to survival.
Survival.
Yeah, because we are dealing with extreme voltages at a power plant. These stationary windings are dealing with voltages ranging from 6,600 volts up to 33,000 volts.
Oh, wow. So if you try to spin 33,000 volts at thousands of RPMs, that sounds like an immediate recipe for a catastrophic electrical arc or just a massive fire.
It is a nightmare for insulation. I mean, it is significantly easier to properly insulate those thick, high-voltage wires when they are firmly bolted down and perfectly stationary.
Right, makes sense.
Furthermore, if a short circuit happens on the grid, these windings are suddenly subjected to intense, violent electromagnetic forces that physically try to twist the metal.
Oh, geez.
Yeah. Because they are the stationary stator, they can be heavily braced and structurally secured against a massive cast iron frame. If they were spinning, well, the combination of those short-circuit forces and natural centrifugal force would literally tear the copper windings apart.
But wait, I have a mechanical question. What about the spinning part, the rotor? You said it's a magnet. But in a power plant, that's not just a giant permanent fridge magnet, right?
No.
It's an electromagnet, which means it needs its own electricity to work.
Right.
How do you get power onto a spinning metal shaft without the wires getting tangled?
You do need to power the rotor, but it only requires a relatively small amount of low-voltage direct current, usually between like 100 to 500 volts, to excite the field winding and create that magnetic field.
Okay, so a lot less dangerous than 33,000 volts.
Exactly. To get that low-voltage DC power onto the spinning rotor shaft, you just use two simple, smooth metal rings on the shaft. They're called slip rings.
Yeah.
And you have stationary brushes pressing against them. It's mechanically and electrically just infinitely simpler to slide 500 volts onto a spinning ring than it is to try and extract 33,000 volts off of one.
So we have this massive stationary cage of copper wire, the stator bolted to the floor.
Yeah.
The entire trick to powering the modern world is just figuring out how to violently spin a magnet inside that cage.
That's the essence of it, yeah.
Which brings up a huge question. Are all these spinning magnets built the same way? Like, is there just one standard industrial rotor that every power plant buys out of a catalog?
Not at all. The entire design of the rotor is completely dictated by its prime mover.
Prime mover, meaning the thing that is physically doing the pushing,
Yeah.
like the water or the steam.
Exactly. The source of mechanical power. Because prime movers behave very differently. We have two drastically different types of rotors.
Okay, what are they?
You have the salient pole rotor and the cylindrical rotor.
Okay, salient literally means sticking out or protruding. So a salient pole rotor has parts physically sticking out of it, like a giant metal paddle boat wheel.
That is a highly accurate visual, actually.
Yeah.
Imagine a central steel wheel with massive, heavy magnetic poles physically jutting out from the center shaft, almost like thick spokes.
Wow.
These rotors are massive in diameter. They can be incredibly wide, but they are relatively short in their length.
I'm picturing these massive chunks of metal sticking out of a machine that is supposed to spin. That sounds terribly unaerodynamic and incredibly clunky. Why would you ever design a high-speed machine that way?
Well, you wouldn't use it for high speed. You use a salient pole rotor when your prime mover is exceptionally slow.
Oh, okay.
Think of a massive water turbine at a hydroelectric dam. A river is incredibly heavy and possesses immense force, but it spins that turbine very, very slowly compared to something like high-pressure steam.
Right. Water is dense. It's a slow, unstoppable grinding force.
Exactly. But here is where the physics get tricky. The power grid in your house demands alternating current at a very specific frequency, usually 50 or 60 hertz, depending on your country.
Right.
To generate that exact 60 hertz frequency when your rotor is barely spinning at, say, 100 revolutions per minute, the physical equations dictate that the rotor needs to have a huge number of magnetic poles sweeping past the stationary wire to make up for the slow speed.
Oh, I see.
Sometimes you need dozens of magnetic poles.
Ah. And to physically fit dozens of giant magnetic poles around a single circle, that circle inherently has to be really, really wide. Hence the massive diameter of the salient pole design.
Precisely. Hydro alternators accommodate all those poles on a huge diameter, and because they spin slowly, the fact that they have a metal pole sticking out isn't a problem.
Okay, that makes sense.
But on the exact opposite end of the spectrum, you have cylindrical rotors. These are perfectly smooth, solid cylinders forged from a single, high-grade block of steel.
Like a metal log.
Yeah, exactly.
Yeah.
They have a very small, narrow diameter, but they can be incredibly long.
Okay, if the cylindrical ones are perfectly smooth, and obviously have incredible dynamic balance because they're basically solid steel tubes, why not just use them everywhere? Like, why bother with the clunky paddle boat ones?
Because of the terrifying reality of centrifugal force, cylindrical rotors are used for turbo alternators.
Turbo alternators?
Yeah. These are driven by high-speed steam or gas turbines spinning at mind-boggling speeds, typically 3,000 or even 3,600 revolutions per minute.
Right. Centrifugal force is what pushes you to the outside wall on that spinning gravitron ride at the state fair. But we are scaling that force up to massive industrial steel blocks spinning 60 times a second.
Exactly. If you tried to take one of those wide paddle boat style salient pole rotors and spin it at 3,000 RPM, the sheer outward centrifugal force would literally rip those protruding metal poles right off the central shaft.
Oh, man.
Yeah, the entire multi-ton machine would violently explode like a bomb. So to survive those speeds, engineers must use a sleek, narrow, solid cylindrical rotor.
Because there's nothing to rip off.
Exactly. And because it spins so fast, it only needs 2 or maybe 4 internal magnetic poles to perfectly hit that 60 hertz grid frequency.
So to synthesize this,
Yeah.
the power keeping your smartphone charged right now was born inside a massive steel cage. And inside that cage, either a slow, towering water wheel is grinding away, or a sleek, solid steel tube is screaming at 3,000 RPMs, pushing magnetic fields through copper wire to generate megawatts of power.
It's quite a picture, isn't it?
It really is, but, I mean, the sheer mechanical friction and the electrical energy of that must create an absolutely catastrophic amount of heat.
You've hit on what is arguably the single biggest limiting factor in all-electric machine design, which is thermal destruction.
Wow, thermal destruction.
Yeah. When an alternator or a transformer is operating, it generates a massive amount of internal heat. And it primarily comes from 2 unavoidable electrical sources.
Let me guess, is one of them just the physical friction of pushing that much electricity through a wire? Like, pushing too much water through a narrow pipe?
Spot on. That is known in engineering as I squared R loss, or copper loss. It is the heat generated by pushing electrical current through the natural physical resistance of the copper windings.
Okay.
The harder you push the current, the hotter the wire gets, exponentially. But the second major source is arguably more fascinating. It's called core losses.
Core losses, meaning the heavy iron frame of the machine itself gets hot, even if no electricity is flowing directly through the iron.
Yes. The heat manifests directly inside the steel magnetic core. It is a combination of 2 things. First is hysteresis.
Hysteresis.
Right. Think of the iron core as being made of billions of microscopic magnetic domains. Because it's alternating current, the machine is forcing every single one of those microscopic magnets to physically flip their direction 60 times every single second.
Oh, wow. So it's literally internal atomic level friction. The metal is heating up because its own molecules are being violently shaken back and forth.
Exactly. That atomic friction generates immense heat. And the second part of core loss is eddy currents.
Eddy currents.
Yeah. These are little unwanted swirling tornadoes of electricity that get accidentally induced inside the solid metal core. They do absolutely no useful work. They just swirl around and generate pure heat.
It's highly ironic when you step back. I mean, these machines are the absolute pinnacle of human engineering, built specifically to create useful power for society, yet a massive percentage of the engineering involved is dedicated purely to managing their own highly destructive byproducts.
It is a constant, unyielding battle. If that heat isn't actively removed, the insulation simply melts, the copper touches the steel, and the machine violently short-circuits and dies.
Which is bad.
Very bad. So the methods for cooling these machines scale up drastically.
Wow.
For smaller machines, you have air natural cooling, which is literally just letting ambient air drift over the metal, or air blast, where massive fans force air through the core.
Like the cooling fan spinning up on my laptop when I open too many tabs, but, scaled up to the size of a house.
Correct. But for those giant synchronous generators at power plants, simple air isn't remotely enough. The friction of the air itself rubbing against a rotor spinning at 3,000 RPM creates too much drag.
Oh, well, the air becomes the problem.
Yes. So they completely seal the generator and pump it full of highly pressurized hydrogen gas.
Wait, hold on. You're telling me they take a machine generating 33,000 volts of electricity, enough power to vaporize a human being, and they fill the inside of it with hydrogen gas.
I know. Oh.
The exact same highly flammable gas that blew up the Hindenburg. How is that an accepted engineering practice?
It sounds totally counterintuitive, but hydrogen is actually an incredible coolant. It absorbs and transfers heat significantly better than air, and because it is much less dense than air, it drastically reduces the physical drag or windage friction on the spinning rotor.
Okay, but the explosion risk.
Right. It requires incredibly complex, airtight seals to prevent oxygen from getting in and causing an explosion. But the efficiency gains are so massive that it is the standard for large plants. It's actually a huge part of future efficiency trends, too, finding even better ways to manage those seals and pressures.
That is deeply unsettling, but also brilliant. But surely hydrogen has a limit, right? What happens when the machine gets even bigger?
When hydrogen isn't enough, we turn to the ultimate coolant, which is direct water cooling.
Okay.
For the absolute largest utility generators, engineers actually use hollow copper wires for the stator. They pump highly purified, deionized water directly through the inside of the live 33,000-volt copper conductors to carry the heat away from the inside out.
Pumping water through the center of a live high-voltage electrical wire. That feels like it breaks every single rule of electricity we learn as children.
It does, which is why the water must be perfectly deionized. Pure water actually doesn't conduct electricity well at all. It's the minerals in standard water that carry the charge.
Oh, interesting.
Yeah, so by keeping the water perfectly pure, they can run it right through the live electrical elements safely.
Okay, so we've managed the impossible, we've generated the power, we've prevented the alternator from melting into a puddle of expensive slag using forced hydrogen and hollow water pipes.
Yes.
But now that raw, massive power is just sitting there at the power plant. How do we get it hundreds of miles away to my house or to a massive manufacturing plant without losing it all along the way?
That is where the unsung hero of our modern electrical grid comes in, the transformer.
Right.
A transformer is a completely static device, meaning it has absolutely zero moving parts. Its entire job is to transfer electrical energy from one circuit to another using magnetic flux without changing the frequency of the power.
I've always struggled with visualizing transformers. A lot of people compare them to like a bicycle gear system. You shift into a low gear on a hill, you pedal faster, but you get more torque. You trade speed for pushing power.
That's a common analogy.
But that analogy completely ignores how the transformer actually works, because there are no physical gears touching each other in a transformer.
Yeah.
The wires don't even touch.
And that's the magical part of it. A better way to visualize the mechanism of a transformer is to imagine two completely separate rooms divided by a thick pane of glass.
Okay, 2 rooms, glass window.
Right. In room A, you have a crowd of people shouting. The sound waves hit the glass, causing the glass to violently vibrate.
Got it.
In room B, those vibrations push the air, and a new crowd hears the sound and starts shouting, maybe at a higher or lower pitch, depending on the shape of the room. No air ever crosses between the rooms.
Wow.
No electricity directly crosses between the wires in a transformer. The energy crosses invisibly through the vibrations in the glass.
And in the transformer, the shouting is the alternating current, the glass window is the solid iron core, and the invisible vibration crossing the room is the magnetic flux.
Exactly. Through the ratio of the number of wire turns wrapped around that iron core, a transformer can step up the voltage, which mathematically forces the current to step down.
Okay.
Or it can step down the voltage, which forces the current to increase. And this ability to effortlessly trade voltage for current is the only reason a long-distance power grid is physically possible on planet Earth.
Let's connect this back to the heat problem.
Yeah.
You step up the voltage to drop the current. And earlier, you said that current is what causes that I squared, or friction heat loss, in a wire.
Yes.
So if we want to send power across the country without it all burning up as heat on the highway, we have to kill the current.
You've perfectly synthesized the engineering logic. Transmission losses on power lines are proportional to the square of the current. If you push high current over hundreds of miles, the wire just turns into a giant space heater and wastes all the energy.
Which is terribly inefficient.
Exactly. So power transformers at generating stations step up that generated 33,000 volts to extra high levels, like 230,000 volts, or even ultra-high voltages above 750,000 volts.
That's insane.
By forcing the voltage that incredibly high, the current drops to a tiny trickle, and the massive power can safely travel across the country on relatively thin metal lines with almost zero thermal loss.
But obviously, you absolutely do not want 750,000 volts coming out of the wall socket in your kitchen when you plug in your coffee maker.
No, that would be completely lethal. That's why, at the destination, we use distribution transformers.
Are those the gray metal cylinders on power poles in your neighborhood?
That's them. They catch that transmission voltage and step it back down in stages, trading that high voltage back into usable current, finally delivering a safe, manageable 120 or 240 volts to your home.
That brings us perfectly to the human element. Delivering this massive high voltage across the country is incredible for efficiency, but eventually, human beings have to physically interact with this system.
Yep.
Human operators sitting in control rooms at substations
Right.
or, workers in massive industrial facilities. How do they do this safely? Because if I'm an engineer, I can't exactly just plug a standard multimeter into the 33,000-volt power line to check if the power is flowing correctly.
No. Doing so would instantly vaporize the instrument, the wires, and likely the operator holding them. The physical insulation required for a measuring dial to directly handle 33,000 volts would be the size of a small car.
So what do they do?
This introduces a critical safety tool, which are instrument transformers, specifically current transformers, or CTs, and potential transformers, PTs.
Wait, I want to clarify something here. In industrial settings, they talk about power flowing through a bus bar. A bus bar isn't just a regular wire, right? We're talking about those giant solid middle logs you see at substations.
Yes. A bus bar is a thick, solid strip or tube of copper or aluminum that conducts massive amounts of local current. Let's say you have a bus bar carrying 5,000 amps of current. A current transformer will physically clamp around that massive bar, and using that exact same magnetic flux principle, it will step that lethal 5,000 amps down to a tiny, standardized, mathematically proportional fraction, usually just 5 amps.
So the human operator sitting at a desk in the control room is completely physically isolated from the danger. The dial they're looking at is only experiencing 5 amps of gentle current, but they know it perfectly represents the 5,000 amps raging outside.
Precisely. The operator and the delicate digital measuring instruments are entirely separated from the lethal high-voltage circuit. Without instrument transformers, operating and monitoring the modern grid safely would just be completely impossible.
And what about heavy manufacturing? I know a massive amount of the power generated isn't just for lighting up homes, it's to power heavy industry.
Yeah, heavy manufacturing relies on a very specific variation called an autotransformer.
Autotransformer.
Right. Unlike a standard transformer, which has two completely separate coils of wire insulated from each other, like our two separate rooms with the glass window, an autotransformer uses just one continuous single coil of wire that is physically tapped at different points.
Just one coil. That implies you are using roughly half the copper wire. That must be incredibly cost-effective and efficient.
It is highly efficient. Because it shares the windings, they have better voltage regulation and save massively on copper conductor material. In heavy industry, autotransformers are used extensively to safely start up massive, power-hungry industrial induction motors.
Wait, why do you need a specialized transformer just to turn a motor on? Can't you just hit the on switch and give it the full grid voltage?
If you try to hit a gigantic factory motor with full grid voltage right from a dead stop, you run into the physics of inertia.
Oh, because it's heavy.
Right. The motor isn't spinning yet, so it provides almost zero electromagnetic resistance. It acts almost exactly like a dead short circuit. The sudden, massive inrush of current trying to force a multi-ton piece of steel to instantly start spinning could literally melt the motor windings, or it could pull so much power so fast that it crashes the local power grid's voltage for the entire neighborhood.
Ah, so it dims the lights for the whole block.
Hmm?
So the autotransformer steps in, drops the voltage, and gives the giant motor a gentle, low-voltage nudge to get that massive steel rotor moving safely. And once it has some momentum, it switches over to full power.
Exactly. It manages the physical transition safely. The electric machine isn't just the giant generator sitting in the power plant. Specialized versions of it are doing the delicate, heavy lifting at the final destination, too.
It really is awe-inspiring when you step back and look at the entire chain of events. We start with the incredible mechanical engineering of a rotor. Whether it's a massive, clunky salient pole catching the immense, slow weight of a river, or a sleek, solid cylinder screaming along on high-pressure steam.
It's quite a journey.
Yeah, and we convert that violent motion into electricity, battle the immense atomic friction and heat with hydrogen and water, and then feed it into transformers. And those transformers act like the invisible gears of the grid, stepping power up to fly across continents, and stepping it down so we can safely start a factory motor or just, boil water for tea.
It is a continuous, exquisitely balanced ecosystem of energy conversion. But before we finish, I want to leave you with a fascinating philosophical paradox straight from Ashfaq Hussein's manual.
Oh, I love a good engineering paradox. Lay it on me.
Well, in the very first chapter, before diving into the complex math, the manual spends time rigorously defining what it calls an ideal transformer.
Okay.
It lists the required properties. The iron core has infinite permeability, meaning the magnetic flux flows through it perfectly with zero resistance.
Sounds great.
The primary and secondary copper windings have absolute zero electrical resistance. There is zero leakage of the magnetic field, and there are absolutely zero power losses due to heat, hysteresis, or eddy currents. It operates at exactly 100% efficiency.
No resistance, perfect flux, zero heat. That sounds absolutely perfect. I want one for my house immediately.
Well, that's the paradox. Immediately after laying out all the math for this perfect machine, the manual flatly states that an ideal transformer is strictly an imaginary machine.
Wait, what?
No practical commercial machine has these properties. It simply does not exist in our universe.
Wow. They meticulously define the absolute perfect machine, mathematically prove how it works, just to tell the reader that they can never, ever have it.
Exactly. It leaves you to ponder something fundamental about the reality of engineering.
What's that?
The entirety of the modern electrical grid, this massive world-spanning organism of generation, transmission, and safe distribution we just explored, isn't actually about achieving perfection. Perfection is physically impossible.
Right.
Engineering is actually a brilliant, never-ending battle to manage, calculate, and elegantly design around nature's inevitable imperfections, friction, and physical limits.
That is wild. We demand the absolute magic of the flip of a switch, completely unaware of the roaring, imperfect, heat-generating monsters required to make it happen. The grid isn't perfect. It's just perfectly managed chaos.
Very well said.
Next time you turn on a light or plug in your phone, just think about the incredible balancing act going on hundreds of miles away behind the walls to get that power to you. Thanks for joining us on this deep dive. See you next time.